All right, so let's finish up answering the question, how many ways are there to color the faces of the cube that end up being visually distinct after you account for all of the symmetries that we talk about? All right, so I have filled in where we left off last time, which is I've calculated here the cycle number of each of the types of symmetry. And so last time we left off, and I encouraged you to calculate these yourself, but let's really quickly look at the single face rotation. So when I take a single face rotation, what's going to happen is that the blue piece is going to go there. If I do it again and again and again, and so what's happening is the blue face is traveling all the way around the cube and occupying the space of all of the faces other than this one on this side and this one on this side. Okay. So these four faces form one orbit under the single face rotation. Okay. On the other hand, under this single face rotation, this face never moves, and this face never moves, which means this is one orbit, this is one orbit, and then all four of these faces are one orbit. So what that means is that in total, there are 3 orbits, so that's where this 3 comes from. Okay, now what happens with the double face rotation? Here's what we have to figure out. Why is this different? And here's why. If I apply the double face rotation, I end up here, and then I apply it again, I get back here. What's happening is that the double face rotation is exchanging the blue and green face, and it's exchanging the white and yellow face, but it's not mixing up the blue face with the white face or the blue face with the yellow face. So in fact, actually, the blue and green faces are in one orbit. The white and yellow faces are in one orbit. And then again, we have the orbit of the front face because it never moves, and the orbit of the back face because it never moves. So in total, that is 1, 2, 3, 4 orbits. And that is where this 4 cycle number comes from. Okay. So with that, we can calculate, again, this formula from the Polya enumeration theorem, namely, the number of colorings is going to be 1 over the size of the group. Oh, so in this case, that's going to be 24, times the sum over the group elements of the number of colors to the cycle number power. Okay. So I want to do that, and so I'm going to actually answer the question here, how many ways are there to color a cube in M colors? So I'm not going to specify the number of colors in advance. And then once I've done that, then we can go ahead and calculate it for, say, 2 and 3 colors. So how many ways? We color the faces of a cube in M colors. Okay. So, what am I going to need? Well, I'm going to get the sum across the symmetries of M to the cycle number of G. Okay. And I can rewrite this as 1/24 times. Okay, and now I'm going to go type by type. And I'm going to need 2 pieces of information here. I'm going to need to know what the cycle number of that type is, and I'm going to need to know how many of that type there are, both of which are things we calculated in the previous video. So when I do this, first I'm going to do the identity. There is one identity, and that's going to contribute an M to the cycle number of the identity, and the cycle number of the identity is 6. Okay. But then we're going to have plus, and so then we have to look at the edge rotations. There are 6 edge rotations. Each of them has a cycle number of 3. And so what that means is that I'm going to get 6 times m cubed. Okay, continuing on the next line, we have the diagonal rotations. There are 8 of those. Each of them has a cycle number of 2, so that is going to give me a contribution of 8 times m squared. Plus, okay, and finally, you can look at your sheet of paper. For the single face rotations, there are 6 of them. And they have a cycle number of 3. Plus, finally, we have the double face rotations, of which there are 3, and they have a cycle number of 4. All right, and so that means the number of ways to color a cube, color the faces of a cube in m colors is 1/24 of m to the 6th plus 3m to the 4th plus 12m cubed plus 8m squared. Which is maybe not the most beautiful thing you've ever seen, but it's pretty cool, actually, I think, that this ends up being, of all things, a degree 6 polynomial in M. It's definitely worth remarking that this thing, given that it's an integer divided by 24, is not at all obviously an integer. But if we believe the theorem, we know this is an integer. And we can go ahead and calculate this for 2 and for 3. And when you calculate it for m equals 2, okay, that is the number of ways to color the faces of a cube in black and white. We're going to get that there are 10 ways. And when you do the same thing for m equals 3 colors, then you'll find that there are 57 ways to do this. And you can answer this question to your heart's content with any number of different colors. Okay. For the homework question for this video, I'm going to ask you to do the same calculation, but instead of coloring the faces of a cube, we're going to imagine that you have a wireframe cube. That is, the faces are gone, and the only things you see are the edges. And I'm going to ask, how many ways are there to color the edges of the cube in m colors? So note there are 12 edges. I'm asking you how many of them you can, or how many ways there are that you can color those 12 edges. Again, you're imagining the faces are now gone. Also, we'll do the other thing. So now imagine the edges are also gone. So the faces and edges are both gone. And so now the cube consists entirely of the 8 vertices floating in space in this rigid structure. And so my question then to you is, how many ways are there to color those 8 vertices in m colors? Again, up to all of these symmetries. All right, I'll stop there, and we'll pick up with another example next time.